Let's think of an object going in a circle at a constant angular speed. So it's going at a constant angular speed around the circle. The circle has radius, say, r, capital R. And let's use x and y coordinates. So here is the y direction. This is the x direction. And there's some angle theta. That angle is changing. Here's the object. And it goes around at a constant theta dot. So that's the time derivative of the angle. That's constant. So let's look at this from a Lagrangian perspective. So we have coordinates x, and the x value of this position is just r cosine theta. And the y value is r sine theta. And so we need time derivatives, x dot, y dot. X dot is theta minus theta dot r sine of theta, and the time derivative of y is theta dot r cosine of theta. And so we can build Lagrangian, right? So there's no potential energy. So the object is, say, on a horizontal surface. Doesn't have to be. It's just going at a constant angular speed. We can think of it as moving on a table where all the forces are balanced in this direction. Of course, there is a centripetal acceleration, which at this point here is that way. And we would see that if we took second derivatives of x dot and y dot. Those aren't zero. It's just that, well, we might as well write them down. So x double dot involves time derivative of this, but that just brings out another theta dot. So we have theta dot squared, and we turn this back into a cosine. And here, similarly, we have, but we bring a minus sign for the derivative of the cosine, so we have theta dot squared r sine of theta. So there's definitely an acceleration. It's not an acceleration in the angular coordinate theta. So the Lagrangian is kinetic minus potential. So we have t minus u. There's no potential, so we have kinetic. Let's say the mass of the object is m. So we have m over 2 x dot squared plus y dot squared, which is m over 2 times theta dot squared r squared sine squared of theta plus theta dot squared r squared cosine squared of theta, which is just m over 2, right? Theta dot squared r squared can be pulled out, and so we just have sine squared theta plus cosine squared theta in parentheses. That's equal to 1, so we simply get theta dot squared r squared. That's the Lagrangian. So dl by d theta is, of course, equal to 0 because there is no theta in the Lagrangian. And so right, the other term is d by dt, dl by d theta dot, and that's equal to this, so that must be equal to 0. So it must be the case that dl by d theta dot is equal to a constant. So there is a conserved quantity, which is dl by d theta dot, and so we see that it's m theta dot r squared. That's a constant. Right, that quantity isn't changing, and unsurprisingly, it's the angular momentum about the center of the circle, right? We can see it's just the tangential speed vt is equal to theta dot r, and so we see that we have the magnitude of the angular momentum is m v tangential times r, and that's unchanging.